Okay, good morning. Sorry I had to leave for a couple of minutes. I had left my notes in the office. Okay, let's get started, please. You can have your discussion after class. I want to get through the 5 examples for today. The first 4 I want to get done within the first 25 minutes. And I apologize, I left my notes in the office, so a couple of minutes over time. All right, let's see. Let me share. Zero two. All right, example 1. The first 2 examples are with regards to sinusoidal phasors. So let's see how we solve this. Back. There we go. All right. So the first thing is given to us as V of t is 10 cos omega t plus 10 sine omega t. All right. It's asking you to find the value of the voltage as a function of time. So your final answer should also be as a function of time. Okay. This is the problem statement, and it is simply asking you what the sum of these 2 sinusoids would be. So your final answer should also be as a function of time, not as a phasor. All right, so first step is that we have to convert sine into cosine. Okay, we cannot write or we cannot perform a phasor transform without converting the sine to cosine. So this sine omega t becomes cos omega t minus 90. The first term remains the same, 10 cos omega t. This one, we subtract 90 degrees from the phase. Originally, the phase is 0, so this simply becomes minus 90 degrees. Cosine. Cos omega t minus 90. Okay. So that's the first step. Actually, even before that, there's one more step that we have to, or there's one more point we need to take into account. In order to add or subtract sinusoidal waveforms, the frequencies must be the same. You cannot perform addition or subtraction of 2 or more signals if their frequencies are not the same. Okay. So that's the absolute first step you should consider. In this case, in these examples, we are simply given omega, right? There's no other value given to us. Omega value is not given, F is not given, but it doesn't matter because the frequency omega has no effect on the phasors. And so when you perform this mathematical operation, omega doesn't matter at all. Okay, so now we write down the phasor directly. Phasor for Vs is 10, magnitude 10, angle 0. Second term also has magnitude 10, the phase angle of minus 90. You directly write down the phasor transform, or directly write down the phasor from the cosine function. Now at this point, I would tell you that if you have a calculator and you are able to program this, go ahead and do so. It'll give you a final answer directly. Okay. So again, if you have not yet practiced, this is a good time to do so. Go ahead and program this equation in your calculators and see if you can get the final answer. If you have a scientific or engineering calculator that is not programmable, like mine, but it can still perform polar to rectangular conversion, then that's what I do. I perform the conversion back and forth between polar coordinates and rectangular coordinates. Worst case, if you do not have any sort of scientific or engineering calculator, you can still use trigonometric identities to perform these math functions on a simple calculator. Right? The phasor the phasor, the polar coordinates of the phasor, the magnitude and the phase angle, relate to the rectangular quantities by the trigonometric identities. It's a right angle triangle, right? It's a right angle triangle. So sine x and cos x would give you all four sides plus the phase angle. So if you have any two quantities, you should be able to solve for the other two. Right now, I won't show you how to do so, but I will post a note sheet online, which will have all those equations. Anyway, so right now I want to perform addition. So I'm going to convert this into rectangular coordinates, which simply gives me 10 plus J0 plus 0 minus J10. Right? I want to perform manual addition or subtraction. It's easier to do so in rectangular coordinates. Add the real parts together, add the imaginary parts together, and you get 10 minus J10. Convert this to polar coordinates because we want to perform a inverse phasor transform, meaning our final answer should be as a function of time. So from rectangular coordinates, I'll go back to polar, 14.14, the phase angle of minus 45. And from here, you can directly write down the time domain answer. Vs of t has a magnitude or a peak value of 14.14. Cos of omega t. The frequency does not change. It's important to keep in mind. This mathematical manipulation does not affect the frequency at all. The frequency remains the same. So it's cos omega t with a phase angle of minus 45. And then, of course, volts. And that should be your final answer. Okay. If the expression asks, if the question asks you to find Vs of t or I of t as a function of time, you have to perform the inverse transform at the end. It's simply one additional step. You take the cosine expression, you take the phasor that you obtain at the end of your solution, you take the magnitude and you take the phase angle and you directly write down the inverse phasor transform. It's as easy as that. And again, if you had a programmable calculator, you would go directly from this step to here. So yeah, it's a right angle triangle. So the conversion from rectangular to polar and polar to rectangular, you can do it manually using trigonometric identities. For instance, if you have, this is the phasor, right? This would be the real component. This would be the imaginary component. So if this was R with the phase angle theta, so out of those four conversions, I'm just showing you one. R with the phase angle theta, that was the phasor we had initially, and we wanted the rectangular coordinates. We could simply write tan inverse of theta is the imaginary versus the real value. So we just use trigonometric identities to perform the conversion between the two. But this is only if you're stuck and you don't have a scientific or engineering calculator handy. I just show this so that students should be, as engineers, you should be aware of this. This is, I guess, I don't know, basic trigonometry. So again, all engineers should be aware, right, of this. But there is no, I don't envision a scenario where an engineer would not have a calculator handy. Anyway, 10-second pause. Let me know if you have any questions. And it works for voltage, current, subtraction, addition, right? We're simply adding two phasors. Okay, any questions? Shall I move on? Okay. All right, example 2. We have the same thing. We're asked to find the sum of V1 of t and V2 of t. In this case, the phase angles have a value not equal to 0, but it doesn't change our approach. The approach remains the same. So I would write out my expression. Vs of t is 20, and I'm directly writing down the phase angle. This would be minus 45. That's the first term, V1 of t, plus, if I convert this, it would be cos of 60 minus 90. So it'd be minus 30. Minus 30 degrees. 60 minus 90. I'm performing the cosine conversion. Sine x is equal to cos of x minus 90. Since I need the expression in cosine format, I subtract 90 degrees from the phase angle. Phase angle is 60. 60 minus 90 minus 30. Is everyone clear on that? Right? Okay. Then again, this is a one-step answer. If you can program this into your calculator, you can directly write out the final answer. But if you want to do it manually, then I would convert this into rectangular coordinates. J 14.14 plus 8.66 minus J5. And then the sum of the real components comes out to be 22.8. And the sum of the imaginary components comes out to be 19.14. Oh, this should be phasor for Vs, not Vs of t. Phasor for Vs. And then phasor for Vs, 29.77 magnitude with a phase angle of minus 40.0125. And then finally, my answer in the time domain, Vs of t, you directly extract the magnitude from the phasor, 29.77. Expression, the inverse phasor transform would give you a cosine expression. So cos of frequency remains the same. So omega t minus the phase, 40.01 degrees, unit of volts. And again, calculators have made it so easy for us. Technology has made it so easy for us. It's typically a one-step answer. Okay, it's a one-step answer. All right, yes, questions? Mm-hmm. Yes. So this is 20 with an angle of minus 45 here, and this is 10. And since I want cosine, I would be 10 cos omega t plus 60 minus 90. So that gives me peak value magnitude of 10 with a phase angle of minus 30. That's where it comes from. Yeah. All right. Any questions? Any other questions? Was there a question from online? Okay. All right. Does that make sense? Right now at simple math, we're only taking two complex numbers and adding them up. Okay. We haven't done any circuit analysis yet. Yes. Yes. You can download the manual, operating manual for your calculator from the manufacturer's website. Well, there are tons of people out there who have like posted videos. You can read tutorials. It's not that difficult to find. And of course, reach out to your fellow peer students. And it's, again, I don't have one myself, so I don't, I haven't ever used a programmable one. In real life, as a practicing engineer, you will have access to software tools. You would still simply be able to like program it in MATLAB. It will spit out an answer. There'd be many other software tools you could use. There are actually online calculators on websites. You can simply enter the coordinates. It will give you a final answer. Obviously, during an exam, you won't have access, to website. So as an engineer, of course, it behooves every single one of you to know how to perform this operation. Okay, it's 9:28. Let's get through this example 3. All right. So inductor value is given to us as 0.25 Henry. We are given the applied voltage, VL of t. We are asked to find the current. Okay. Example 3. Inductor value is given. Voltage is given. So again, my standard line to students is always look at the problem statement, including the circuit diagram, and then extract as much information as you can. So the summary of this is that the given values are the inductor and the voltage. And we are asked to find the current, I. Now think back to chapter 3. What do we need to do to find the inductor current from the inductor voltage? Inductor voltage is L di over dt. So inductor current, if you need to find inductor current, typically you would integrate the voltage 0 to t. Anyone remember that? 2 chapters ago. But because you're using phasor transforms, we don't have to do any of that. You would simply find the impedance, apply Ohm's law, perform the complex math, or perform the simple math with complex numbers, and you find current directly. Okay, so there are 3 quantities. Even if only one quantity was asked of you, you would still have to find the impedance to solve the problem. Okay, so this is incorrect. It should not be VL of t because VL of t is given to us. Okay, so the first thing I would do is I would write up the phasor for VL. And that would simply give me 100 with an angle of, why is my magnitude 100, phase angle 0 volts. Okay. ZL is simply omega L with an angle of 90 degrees, or it is J omega L in rectangular coordinates. Typically, I find both at the same time, which is not that difficult to do. Omega is 200. So omega is 200 radians per second. That is the information given to us. And I can write ZL as 200 times 0.25 with an angle of 90 degrees. And so that comes out to be 50, magnitude 50 with an angle of 90 degrees. In rectangular coordinates, it would simply be, what is it, omega L, so it would be J50, right, J50. And unit is ohms. So 50 with an angle of 90 degrees, or in rectangular coordinates, it would simply be J50. J50 ohms. Since I need to perform a division, it makes sense for me to keep it in polar coordinates. Remember, applying Ohm's law, V equals IZ, I can find the phasor for IL as VL over ZL. VL is 100 with a phase angle 0. ZL is 50 with a phase angle of 90 degrees. So my answer for IL, phasor for IL is 2, magnitude 2, with a phase angle of minus 90 degrees amps. Does that make sense? We are given the inductor voltage, we are given the value of the inductor, and we are simply asked to find the inductor current. By using phasor transforms and complex numbers, it's a one-step answer. You're simply applying Ohm's law the way you did in chapters 1 and 2 and finding the current. You do not have to solve differential equations, perform integration or derivation as we did in chapters 3 and 4. All right, questions? Any questions about the process? Does this make sense? On why we are using complex numbers? Yes? No? Yeah, there are many cases like that. Yes. There's one more step remaining because the final answer is asked of us as a function of time. So we perform an inverse phasor transform. We take the magnitude 2 cosine or cos of omega t, which is 200t minus 90 degrees amps. Okay, that's your final answer. All right, if there are no questions, let's look at the one for capacitor, kind of a similar solution. We are given a capacitor with a value of 100 microfarad. Voltage for the capacitor is given to us, 100 cos 200t. We're asked to find IC of t. It's the exact same procedure. So example 4, I'm going to write the phasor for VC 100 with an angle of 0 volts. Omega is 200 radians per second. Phase angle theta is 0. ZC this time is 1 over omega c with a phase angle of minus 90 degrees, or 1 over j omega c in rectangular coordinates. So 1 over j omega c. ZC is 1 over omega c, so 200 times 10 microfarads with a phase angle of minus 90. That gives me 50 minus 90 degrees ohms. Okay. Again, remember, these are all equations you can have on your equation sheet. You should simply know how to use them. So once I have impedance for the capacitor, apply Ohm's law. IC is VC over ZC, magnitude of 100, 0 degrees, 50 minus 90, get a value for IC as 2, magnitude 2, the phase angle of plus 90. Final answer is asked as I of t, so we do an inverse phasor transform. So IC of t is 2 cos of 200t plus 90 degrees amps. Oh, yes. Mm-hmm. Where? Oh, yes, it's 100. Yeah. So let's see. Is the capacitor 100 microfarad? Let's see. Okay. Yeah, 100. So it should be here. 100. Oh, that reminds me. The solutions for quiz 6 online. At the final step for part A, instead of using 1 microfarad, I entered it as 10 microfarads. So capacitor value in that quiz 6 solution was incorrect. I'll rectify that error sometime later this afternoon. But the rest of the process in the solutions is all correct. Okay. The only difference is I used a value of 10 instead of 1. Just shift 1 decimal point. Okay, questions. Are we all clear and good on examples 1, 2, 3, and 4? Performing the phasor transform, adding or subtracting 2 sinusoidal phasors, 2 sinusoids, and then solving for current or voltage using phasor transform and a complex number math. Right? It's application of Ohm's law. We're not learning any new analysis technique. Okay, the analysis techniques were learned in chapters 1 and 2. Here we are actually just learning about the mathematical methods. Okay. All right. Example 5. I have 20 minutes to get through this. If you need to leave right at 10, you can do so. If I am not done with this entire problem by then, I will continue on and record the entire lecture. Okay. I mean, record the entire solution. So we are given a circuit RLC, resistor, inductor, and capacitor. Values are given. Voltage Vs of t is being applied, and we are asked to find the current through the circuit, resistor voltage, capacitor voltage, and inductor voltage. One final question is also to draw the phasor diagram. Okay. All right, so let's get started. The first thing we want to do is, if you have a circuit analysis problem like this, is to draw the equivalent impedance diagram. That's what I call it. I call it the equivalent impedance diagram, where I convert each and every component and represent it as an impedance. Okay. So equivalent impedance diagram for this circuit would look like, well, it doesn't look like anything that you haven't seen before. Simply be 3 resistances or impedances. So ZR is of course R, that stays the same. So 100 ohms. This becomes ZL, this becomes ZC. And then this is phasor for Vs of t. So that is simply a phasor transform Vs. It's a series circuit, so current is the same for all. And I would represent that also as the phasor for I. Okay. So if this was chapter 1 and 2 or chapter 2, and you're asked to find the current, what would you do? Equivalent resistance, Req, apply Ohm's law once, find the total current, and then from the total current, you can find the total, you can find the voltage for each individual component, right? The approach, the technique, the analysis of that circuit is exactly the same. That doesn't change. Only the math is a little different, okay? So I would find ZEQ as seen by the source Vs, okay? And so that would be 3 impedances and ZEQ between these two terminals. And because they're all connected in series, ZEQ is simply R plus ZL plus ZC. Okay, R plus ZL plus ZC. Again, this is not something new. You have already seen this. You have seen this in physics. You have seen this earlier in this chapter. In this class. The analysis technique does not change. Only the math is different. So the total impedance for the circuit is from the purely resistive portion R, which is 100 ohms. So I already know what the real component is going to be. It will be 100. Ideal inductors and ideal capacitors do not have any resistance. They have pure reactance, right? We saw in examples 3 and 4, it was J50 ohms. The purely resistive portion was 0. So is the case here. Anyway, we'll take it step by step. First, let's find the phasor transform for the source voltage Vs. And so what we'll do is, all right, let's extract information from here. So Vs is 100 cos of 500t plus 30. So my phasor, I can write directly from there. My peak value, or Vm, is 100 volts. Omega is 500 radians per second. And phase angle theta is 30 degrees. So my phasor for Vs has a magnitude of 100 with a phase angle of 30 degrees. That's it. 100 with a phase angle of 30. Now, I want to find ZL and ZC. So ZL would be either J omega L or omega L with an angle of 90. So it would be 500 times 0.3 Henry with a phase angle of 90 degrees. So that gives me J, sorry, not J, 150 with an angle of 90 degrees. In rectangular coordinates, ZL would be J omega L. So it would be J times 500 times 0.3. This would be J 150 ohms. Or 0 plus J 150. Resistive portion is 0. Make sense? Again, you do not have to do both steps. You can just find either in polar coordinates or rectangular coordinates, your choice. From me, for a habit of so many years, I simply find both at the same time. It's just easier for me to solve problems later on. Okay, later on down the solution. Okay, so then let's find ZC. ZC would be 1 over omega C with angle of minus 90. This would be omega is 500. Capacitor is, what is the capacitor? 40 microfarads. Yeah, 40 microfarads. 40 microfarads. And so this gives me 50 with an angle of minus 90. In rectangular coordinates, this is 1 over j omega c. This comes out to be j into omega 500 into 40 to 10 raised to minus 6. This becomes minus j 50 ohms. Same thing, just different coordinates. Okay. So again, examples 3 and 4, we did the exact same thing. We found the impedance, then we applied Ohm's law. In this case, there's one extra step where you are adding up the impedances. And so again, you add up the impedances. It's simple. It's just mathematics, right? You take your calculator and you add up the three complex quantities and you'll have ZEQ. So since I'm performing addition, what I'm going to do is I'm going to use the rectangular coordinates. R plus ZL, which is J 150, plus ZC, which is minus J50, gives me a ZEQ of 100 plus J 100 ohms. So ZEQ is 141.4 with a phase angle of 45 degrees. The reason I'm converting into polar is because I need to perform a division and multiplication later on. So I'll find both at the same time. So far, so good. Any questions? Any questions at all? Now, at this point, since we need to find the total current, we'll go ahead and find the current. But if I just wish to find the voltage across the inductor, there are a couple of different options, right? I can find the current and apply Ohm's law again, or I can apply voltage division, which still works, okay? Just the math is with complex numbers, but voltage division, current division, analysis techniques, they would still work. Those are fundamental analysis techniques. They do not change. So if you wish to practice both your skills with your calculators as well as your skill with voltage and current division, you can go ahead and do so. And you can compare your answers with the ones we obtain in class. Okay, so ZEQ is 141.4 with a phase angle of 45. Remember, ZEQ is impedance. It's represented as a vector, but it is not a phasor. Okay, it's not a phasor. Okay, current I can be given from Ohm's law. So phasor for I can be written as Vs over ZEQ. Magnitude for Vs is 100. Magnitude for ZEQ is 141.4. Phase angles get subtracted, so it's 30 minus 45. And my answer would be 0.707 minus 15 amps. Minus 15 amps. And since we are asked for the time domain expression for I of t, I will write I of t is equal to a peak value IM of 0.707, cos of 500t minus 15 degrees, and of course amps. Again, it's simply okay. It's simply an inverse phasor transform from the peak values and the phase angle. Okay, so 0.707 cos of 500t. That's the original value of the frequency in the problem, and minus 15 degrees. Does that make sense to everyone? So what would be our next step? We have three components connected in series: resistor, inductor, capacitor. Voltage is applied to that series connection. We applied Ohm's law. We first found the equivalent impedance. Then you applied Ohm's law to find the total current flowing in the circuit, which is the same for every component. Now we wish to find the voltage drop across every component. What do we do? And that's it. We apply Ohm's law again. So V equals IZ. We apply Ohm's law to find the voltage for every single component. So VR, phasor for VR would simply be I times R. Voltage for the inductor VL would simply be I times ZL. And voltage for capacitor VC would be I times ZC. That's it. As easy as that. So I will give you the answers right now. Phasor for VR comes out to be 70.7, the phase angle of minus 15 degrees, volts. Therefore, VR of t, time domain, answer would be 70.7 cos of 500t minus 15 degrees and volts. VL has a value of 106.08, 75 degrees. Therefore, VL of t is 106.08 cos of 500t plus 75 and volts. And VC, phasor for VC, would be 35.35, the phase angle of minus 105 volts. Therefore, VC of t is 35.35 cos of 500t minus 105 degrees. Perform these calculations outside of class on your own calculators and see whether you can arrive at the same answers or not. Okay, that would be a good way for you to practice. So All right, questions? Any questions at all? Does the process make sense? Steps make sense? Fully? You will work with the exact same application no matter what the circuit. Okay, the circuit could be connected in parallel, could be connected in series parallel. Doesn't matter how it's connected, but your procedure and the steps will remain the same. The absolute first step is to convert everything in the circuit and draw the equivalent impedance diagram. When you draw out the equivalent impedance diagram, that would simply give you an assurance that you're not doing anything new. You're simply looking at a problem from like chapters 1 and 2. Okay. Yes. No. Well, not unless there's demand from the students. Anyway. Anyone online want to do mesh current analysis? Node voltage analysis? I do not hear a no, so I would assume that to be a yes. All right. Anyway, as I said, the analysis techniques are not new. It's the math that is new. And so hopefully all of this made sense. Practice outside of your time. I mean, outside of class, not outside of your time, outside of class time. You can also practice this, practice the calculations, but apply voltage division. So you can find VR from voltage division, which would mean phasor for VS times VR or R over ZEQ. VC simply would be VS times ZC over ZEQ. And similarly for VL, it would be VS times ZL over ZEQ. Okay. As I said, voltage division will also work. You simply have to know how to do the math. One last thing remains is the phasor diagram. I have about 30 seconds left. So if you need to leave again, you can feel free to do so. I'll draw the phasor diagram. Let's see. Let me draw it out here on the right. Actually, you know what? Let's keep going down there at the bottom. Okay, so I have tail axis. Okay. What does a phasor need? Phasor is a vector. It only needs two things: magnitude and direction. So the length of the vector is the magnitude of the waveform with the phase angle. So let's first plot out VS. VS was at an angle of 30. So let's see if I plot VS here. Let me use this. I think this is multicolored. That's not 30. It's still probably larger than 30. So let's see. And this is, of course, not to scale. Okay. So this is the phasor for VS. I will write out the phase angles later. VL, I'm going to draw VL and VC with the same color. So VL is about, 75, so 15 degrees away. So let's see. This should be 30 degrees. This should be 75. So VL, again, VL is 75 degrees. So this should be 75 degrees. Okay. And then VC is minus 105. So you go clockwise. Okay. Typical phasors, again, it's a rotating vector that rotates counterclockwise. So you start from 0 and +1, +2, +3. Positive numbers go counterclockwise. Negative phase angles go, positive phase angles go counterclockwise. Negative phase angles go clockwise. So minus 105 would be somewhere here. which kind of makes sense because a capacitor and an inductor would be 180 degrees out of phase. So minus 105. This is minus 105. That's the phasor diagram for these three. VR is minus 15, and so would be the current. So this is VR, and VR is at minus 15 degrees. And the current is also at minus 15. So I'm going to draw that out in blue. I'm sorry, draw that out in red. The magnitude is a little different. So I'm going to stop short right there. And that's I. Again, has the same as minus 15. Okay, so VS, this is VL, and this is VC. And the difference between the current and the inductor voltage is plus 90. And with the, this is 180 degrees out of phase, exactly 180 degrees. Okay. And so that's the phasor diagram for all. Positive phase angle is counterclockwise. Negative phase angle is clockwise. Okay. All right. Again, apologize for going over time. My end class here today. Homework for this, I will make due either, well, I have to check how many problems there are, but most likely Sunday night. So you have Friday, Saturday, Sunday, about 2.5 days. And then quiz on Monday. So I haven't yet decided completely. I'll take a look at the problems and I'll see how long it might take to get through all of it. Okay, I'll bid you a good weekend and I will see you all on Monday for the quiz. I'll be available over the weekend via Zoom for office hours, via email for any questions. So feel free to reach out anytime you need. All right.